Ready? Good afternoon. My name is Kayvan Najarian. Welcome to Tools and Tech. Marcy couldn't make it this week, so wanted me to make the introduction. It's on red.
Oh, okay.
So our main speaker today is Negar Farzaneh. She is a graduate student, Department of Computational Medicine and Bioinformatics. I am co-presenting this session. So what we're going to cover, maybe I should give you like an overview of what we're doing. We're going to have Matlab and Simulink briefly introducing the stuff. So what we will do, we talk about some core capabilities in Matlab, some major functions in Matlab. We go over some simple ones together. Then we talk about the toolboxes that are available in the Matlab, basically the libraries that Matlab has created, and you can use them in your simulation. Then we talk about a couple of toolboxes, and we will go through a couple of examples, practical examples on using advanced toolboxes in Matlab. When we're done with Matlab, we go over Simulink and we talk about like some capabilities in Simulink that might be useful for what we do. So this is a highly interactive presentation. You will see we jump between different topics just to cover as much as we can within the next, 40, 50 minutes. Okay. So Negar, start with Matlab now.
Okay, hi everyone. To start with, the name Matlab comes from Matrix Laboratories. So, as the name says itself, the basic data element is matrix, and we are going to practice everything on features in Matlab also. So, here, let's start with this command. First, we define A as a matrix of with 5 rows and 4 elements. And yes, the random value from 0 to 1. And then we can we make matrix B. Okay, I spoiled everything.
So basically, while she's running that, understand that the reason is just not the name that says Matlab laboratory. It's a style of programming that you can write a program with 100 for loops in it or all kinds of other functions that you have in regular programming tool. But in reality, in Matlab, they have created a system that is highly efficient if we use matrix operations. So understanding the matrix operations and translating your ideas, anything that you want to code, into matrix operation in terms of if and for and other things that you have in regular programming. That's the key thing for Matlab. And I give you an example of like how different the performance would be if you are using mainstream style of programming versus matrix calculation.
Yeah, and most of mathematical functions, which most of them are algebraic functions, are defined within Matlab, so it increases the speed very much. While in other language, programming language like C, C++, you need to define the function in the code, or you should call another package to use those functions. So, as I told you, we make 2 matrices A and B with random variables from 0 to 1. And in the next line, easily we can multiply these 2 matrices. And we can see the product in the command window. And we can add identity matrix to that one using I function. And with that command, we can calculate the determinant and get the inverse of the matrix, which are really fast. And those are built-in functions in Matlab.
So if I can add a comment here, these are elementary functions of Matlab for matrix manipulation. And essentially, whatever majority of the things that you do when you're writing a real program, surprisingly can be reduced to like a few. We just talked about like 4 or 5 of them, but in reality, if you list, I don't know, you go up to 20 and you're done. You can write essentially everything else using these fundamental operations of matrices. I told you that I give you an example. In reality, the performance of a program, a simulation environment like Matlab, deteriorates significantly if you don't follow the policy of matrix calculations. I was running a program when I was a graduate student, and this program was running for week, 1 week of one run. And someone who was master of Matlab, surprisingly, and I was lucky that this thing happened, this mistakenly turned off the machine that I was using. So I lost almost a few days of simulation. But he said in order to make up for that, I'm going to go over your code and make it Matlab related code, right? After these corrections, after using just fundamental operations, this was running for, I think, 20 minutes, right? So there's a huge difference between the philosophy of using matrix in calculations or just doing the regular programming. Negar went through like 4 or 5 of these fundamental operations. I would say there's less than 20.
Okay, and the next feature is vectorized operations in Matlab. And to understand that better, I want to show you and compare non-vectorized version and vectorized version of the code in Matlab. So here in this example, we define x as a vector from -10 to 10. And in non-vectorized, to calculate the second power of each element and put it in another matrix y. In non-vectorized version, we need to define a for loop and calculate the second power for each element one by one. But in and we see the for loop here. But in vectorized version, we can just use one command and do the same thing in one line.
This is the example. This is the perfect example of what I was talking about. So you can essentially use a for loop to create the quadratic function x squared. But this for loop, I mean, this is like just, I don't know, like 20 points or something. But if the operation goes in the order of millions of points or thousands of points, or if you're repeating that multiple times, the time difference between using this overloaded operation squared and that is significant, because this is Matlab, like I said, has a few fundamental matrix operations, and even it's more higher like level of operations in Matlab are based on matrices. So this does a matrix calculation as opposed to this one, which is a for loop.
And the next feature is graphical output, which is optimized for interaction. You can easily make a plot, and here this is the plot from the result of the previous example. And we can change, we can play with properties. We can, here, access properties. We can change the x and y limits. We can change the scale from linear, this is linear now, to log scale. We can reverse it. We can change the color, add labels, and we can rotate the figure easily. So this is one fancy property. And in the next example, I want to show you how we make 3D plots. Now here we make a plane of x and y from -8 to 8 and define z as a function of x. So by using mesh command, we can have the 3D plot. Again, we can play with the properties and we can rotate it in 3D. We can add data types if we want to see the information of one point.
And I can add to that that one of the major capabilities of Matlab is visualization. And there are all kinds of sophisticated visualization techniques that you can imagine. This is like basically simple 3D plot, and even for 3D, Matlab has 6-7 different functions to show you like a two-dimensional function with the third axis in the function. Okay? But one thing that Negar will show later on is that for any one of these functions, if you want to explore similar functions to that, all you have to do is just say help, the name of that function. It will explain that function And in the end, it will suggest similar functions in MATLAB that can be used for similar kind of operation or visualization or anything. So that would be extremely helpful that if you try something in MATLAB, immediately get the help on that function to see what else you can do with that.
Okay. So up to here, we talked about more general functions of MATLAB which are built in. But now I want to introduce you toolboxes which can greatly expand the MATLAB's functionality. These are sets of customized function which can provide you more specialized functionality. And here we can see the list of different toolboxes that are available in MATLAB. For example, we have wavelet toolbox. We have computer vision system toolbox. There are neural network toolbox. There's statistical and machine learning toolbox. But the two main toolbox that I want to talk about today are image processing toolbox and a bioinformatic toolbox. For example, here we see image processing toolbox, and by clicking on that, okay, we can see the complete list of all the toolbox, all the functions and algorithms that are in this toolbox, and we can use them. And the image processing toolbox supports a diverse formats of images. We can read DICOM images, PNG images, and every kind of images using this toolbox. It provides us morphological operations. We can do image segmentation, image transformation. We can use geometric transformation and noising, and every kind of functions that is needed for image processing is provided in this toolbox.
So adding to that, I can essentially remember that MATLAB has very few fundamental functions, but based on these fundamental functions, they create general purpose functions in MATLAB if you want to plot, if you want to do linear algebraic kind of stuff, more advanced ones based on that. And then MATLAB has created very many toolboxes, and not all of them come with the core. I mean, I think none of them comes with the core MATLAB when you purchase that. But the ones that we have, at least I can tell you that for majority of the field of research that we are involved in, there is a MATLAB toolbox, including bioinformatics toolbox that Negar will very briefly introduce it here. But in reality, what these functions do are higher level kind of operations that in each field of study you're more basically interested in. So you don't have to write those major functions if you have access to this library. And like I said, not these libraries are like extra to the MATLAB. So sometimes you don't see. So the libraries that we have in here are not like entire. We have even financial signal processing and financial analysis libraries for MATLAB toolbox.
Okay, so now to work, now I want to show you an example in using image processing toolbox to make a code. And before showing you this example, I want to tell you how images are defined in MATLAB. Actually, each image is defined by a matrix, and each element of the matrix corresponds to a pixel in the image. And the value of that element defines the intensity of the corresponding pixel. And now here, we read an image, and we can show that image here. You see, this is the image of, brain image, which is taken using CT computation, CT imaging. And our goal in this code is to detect and segment the bone skull. Here, with data type, we can see the value of different pixels. For example, the value of this pixel is 112. Another one is 108. The value of ventricles is about 35. The background is 0, and the bone is about 255. So each pixel, as you can see, the intensity of each pixel is defined by the value of that element. And as the value increases, the pixel becomes brighter. And to what?
This is essentially assuming that you have an RGB, right? It assumes that you have red, green, and blue portion for that. But the image that you have in majority of the cases, if you're reading that from the DICOM, it comes at RGB, but R and G and B are all the same. It's basically intensity.
Yeah.
So that's why it says RGB, but the R's and G's and B's are all the same. Okay.
And if they're not the same, we can see colored images. So here, as you see, the value for skull bone is about 255. So what we do is setting the bone threshold to 250, and then find all the pixels that their value is less than that certain threshold to 0 and set them to 0. And all the pixels with value more than that threshold, we find them and set them to 255. And by doing this function, we can have this image.
This is like a simple example of how very high-level commands in Matlab can be easily used to do like a task, basically. So it's a simple application to get the bone in CT images by 3 lines of commands, right? And there's a whole lot more you can do, and she's going to show some of that as well.
Yeah. This is simplified version of the code too. That works for ideal images. And here you can see that there are some artifacts, some noises, so we need to remove them in the next step. And we can easily use Matlab commands to label each disconnected components. For example, this artifact would be labeled as 1, and the skull would be 2, and the other parts get different labels. And okay, in this command, we get the labels for different parts. And in next step, we can calculate the area for each component. And then we're gonna find the component with largest area and take that one as the bone skull. And in the next figure, we can see the result of that one, which all the artifacts and noises are removed from the image.
So basically, So basically, what Matlab gave you in this like 4 or 5 commands was the capability of first thresholding the image, not getting a perfect result, but then inspecting every element that is segmented in the image and filtering them based on the area, saying I want the biggest component in the image that has like a connected region to it, and that would be bone, the skull. So this code is a very simple code, and it's not intended to be like just want to show the capabilities of each of the functions that you see in majority of toolboxes in Matlab. So simplifying what you want to do, but of course you need to know these fundamental functions when you want to change the algorithm as well.
Okay, and next example is a technology that has been developed in our lab using Matlab to process images and videos.
So this is a more advanced. So if you start with this simple project, simple things that we did, you can sort of use more of that and add some algorithms on top of that to do sophisticated tasks and create essentially softwares within Matlab. So this particular one that Negar is doing is an actual project that we do with a group in cardiology. And the objective of the project is to automate the analysis of coronary angiogram. So basically, if coronary angiogram, the task of coronary angiogram is to create a video to show the structure of the blood vessels on top of the heart that give the oxygen, give the blood. So basically, it's a surgical procedure. They insert a catheter, advances to the top of the heart. They release a contrast agent, and as the contrast agent travels through the blood vessels, they're making a video of fluoroscopy. Basically, they have an X-ray machine around the person that makes like a video. Now, the task, the objective of this project is to look at the videos that they create and see if there is a stenosis, if there is blockage inside the arteries. So first you have to analyze the video, identify which are the best frames of the video to analyze, because remember, this thing dissipates. So we read the video, we view the video, and then we start identifying the most important frames, and within those frames, we do some image processing, just like segmentation of bone that we saw. This time we're looking at the artery, blood vessels. So we try to identify those, and then we go through those blood vessels between H2 segments of the image. And we identify the thickness at every point. See, like this. We go through the skeleton that shows the
and then you wrote it away and measured.
Right, and these blue ones are basically perpendicular sort of lines to the skeleton that identifies the thickness of each segment. So it goes from one segment to another, inspects the profile of that segment, and based on the smoothness of the profile, detects whether there is a stenosis or not. If the profile is very smooth, there is no stenosis, meaning that there is no dip in it. But if it says that there is a dip in that, it says stenosis is detected. And the position of the stenosis is also detected, and gives you the percentage of the stenosis, like 70%, 20%, 30%. So this is just one example of MATLAB doing a complete project. For example, remember, this is the catheter that we put in there. We write algorithms in MATLAB to identify the catheter and separate that from blood vessels. And I can tell you, even though it's like a few hundred lines or something, many fundamental things that we need to do on these images, we don't have to actually write it because it's inside MATLAB already. Okay.
So that was one example for image processing and video processing.
The idea would be that this would be a decision support tool that the physician could use in real, that the tech could use in real time.
We're actually, this particular project is saying, or MATLAB altogether.
Using the MATLAB, that's a prototype instrument, but just the output of the chloride, you're trying to take the human out of the loop a little bit.
So we're using that project for two things. One is for quality assessment, because remember, there's like in the recent years, especially the incident in Hopkins, like there was a physician in Hopkins that was overstenting people, and the reason for that is potentially people make more money by saying there is a stenosis there. So if you do angiography and you see that there is a stenosis, you can always misdiagnose and say there is a stenosis and put a stent in people who don't need it. And we have cases.
Very good.
Yeah, right.
So and the problem is that if they stent people, if someone doesn't need a stent at the point and you stent it, it's not that immediately the person's condition deteriorates, right? But remember, these stents, after 3 years, 4 years, they have to go inspected again, and those stents fail. So the person who didn't have any problem to start with ended up paying a lot of money and getting the trouble in 2-3 years after the surgery. There are reported cases of 67 stents, 40-something stents that are put in people, and then peer review of these cases proved that most of these are actually not needed. They were just put people because the surgeon who did that made money. So the first step.
We have a similar thing that's emerging everywhere, and it'll be fun to talk to you about it. It's a fun topic, but anomaly and fraud detection, in medical. Looking at outcomes, and and we just were talking earlier today with the Delta Dental folks. The amount of overbilling and frankly billing for procedures that were never done, in dentistry is catastrophic in this country.
Dentistry is very good for quality investigations, because maybe you have 32 teeth, and each tooth has a number.
Yeah.
And it's very easy to screen. If somebody had tooth number 5 extracted, it's hard to justify paying for its extraction again.
No, you're right.
So basically, the first market that for this thing we considered is quality assessment. But moving forward, if you make that system useful enough for quality assessment and increase the accuracy and predictability of that, it could be used as a computer-aided decision support system. Just like other cases that, as like mammography is an example of that. They're saying either 2 radiologists or 1 radiologist is using a computer-aided decision support system.
Right. So I thought what you were going to say is that working on the quality assessment piece, which is the first step that you're doing when it's a great one, is such an easy transition to quality assurance, which is really related fundamentally to this, doing too many procedures and putting people at risk for these other things. So this is absolutely fantastic. So it fits in very well. What's neat about it is it sits at the translation, because one of the things that we've been learning about our electronic health record systems is they're measurable at reporting outcomes. So if you actually want to machine learn against a electronic health record system, just to have the diagnostic codes in some change in medication longitudinally or whatever, and not being able to see an outcome, in time, clearly, for having to impute outcomes really limits the usefulness of those systems. And so this is going to be something that's really going to help us. This kind of approach to the practice of medicine. So this is really good.
Allah.
So you're saying like improving the quality. So I just maybe other people know that. So what is considered the gold standard? How do you know that it performs well?
Excellent point. I mean, let me tell you, this is like a side project we just wanted to show for introducing Matlab. But now that you ask this question, it used to be that the person who did the angiography was not allowed to immediately do stenting of people, right? They have to show it to like 2, 3 other physicians, get the approval. But now the person who does the angiography can do it immediately after that. They can put a stent. So the policies has changed to make this more like easier to perform, but at the same time, the question is, what is the gold standard? In one effort that we're doing with University of Washington, we're trying to create a huge database of angiograms captured at different places and assign 4 or 5 different cardiologists from different places to go on the web and evaluate them. And then evaluation of these things, average evaluation of these things will become like aggregated evaluation by these physicians becomes the gold standard, right?
So basically, they all agree.
Right, and the good thing about that is that none of these are like retrospective cases, so none of the physicians make really benefit from like saying there is a stenosis or there is no stenosis. So we are trying to, at certain point, create this, but the common practice is that a physician who wants to do that doesn't need approval of anyone else. Just like immediately they can put it. That's why in Texas, in Maryland, there's been a large number of fraud cases, and there is a new policy in Maryland that they have to like submit a good subset of the angiogram to physicians every year for peer review for quality assurance.
And also, I'm wondering, like, I don't like to think that, a physician wants to make money and they would do it where it's not necessary. I think it may be that if they're not 100% sure, it's better to be safe than sorry.
Yeah,
right?
that also is
Because
very,
somebody
very
will
good.
sue them, and I mean, God forbid the patient will,
That's
suffer.
also. I mean, there are other tests that they can order after that just to make sure they look at the flow. So if they're not sure whether this is a stenosis or not, they're supposed to go for the second layer of testing, right?
So I wanted to understand what you're showing us in this arteriogram. The red dots, almost all of them, not all of them, almost all of them are at junctions,
Bifurcation.
bifurcations,
Yes.
which of course is where things happen.
Right.
But is the red supposed to show that there is a constriction or that there is a turbulence? Or what does it show?
No, these red dots are shows branching points or endpoints, and we go from one point to another point and find the diameter, make the profile.
So this is the beginning
So
and
how do you
end of the
identify where there is constriction? Because that's what this is
So
about.
if you
Yeah.
go,
Diameter.
if you go, you see the
Because
blue
it wasn't
things in
real
here. I don't think it's very.
Blue is very hard to see.
Yeah, blue is, so we go through the yellow, and at every point we're saying that where is the like perpendicular line that gets to the edge of the blood vessels, and we measure the diameter, and we have a graph of diameters between each two segments, right? So we say that diameter was relatively
That's
flat.
that plot you had in blue that you
Right,
showed us on the
right,
last slide.
right.
Yeah.
Exactly. If it stays flat, that means that there is no stenosis. But if there is a big dip in it, that means at a certain point the profile became
So the blue is
significantly narrower.
perpendicular to the yellow?
Sort of
Or,
perpendicular.
it looks like it's coming in at a acute
It's,
angle.
it's not always perpendicular because the way we create a skeleton, we cannot guarantee there's always like the exact direction, right? So we start from rectangular, but we like search for like a few degrees before and after to see the actual diameter at that. Just like an algorithm is
Just
more
supposed to
than
be the
one.
internal diameter of the artery.
Yes.
Anybody see that?
So you are detecting constriction between the points.
Yes.
What
The
is
dip
it?
between the
What
two.
is happening at the red point?
At the red points, things are far more complicated because
But usually there are more stuff happening in the red point because it's the junction part, and there will be more turbulence there.
yes, for the flow, yes, but for the stenosis, majority of them are happening along the way. But we have another algorithm. So this part that you're showing is only looking at the middle point. Then we look at the area in here, and we make like another algorithm to see whether there is a stenosis in that region. But that's not as accurate as you want to find it between two segments. I understand your question. Yes. So if you're fine with this, we move on to
The next toolbox.
you want to show another toolbox?
Yes, we have bioinformatic toolbox.
So
to-
very briefly, like in 2 minutes.
Okay, so you can use bioinformatic toolbox to do next generation sequencing, to do microarray analysis, mass spectrometry, and gene ontology, and you can read genomic and proteomic data from standard file formats like FASTA, SAM, CDF, or from online databases like NCBI, Gene Expression, and
So
you can.
So basically, anything that majority of the operations that we regularly do for in bioinformatics, there are codes and algorithms in Matlab in it. So Negar.
Yeah.
You wanna
Show examples.
Yeah.
Okay, and here you can find the examples for all the stuff I told you. Microarray data analysis, there are some examples for mass spectrometry, there are some examples provided by MathWorks. And also it provides statistical techniques to impute missing data and peak detection and for selecting features. And one good feature that it has is that most of the algorithms is implemented in Matlab, so you have access to source code and you can explore them and customize it based on what you're doing.
That's a very important point you make. Like you can access. So these are the pre-ready functions, and these are examples and like library that you have. But you can actually get the code for each one of them. They're open to you, and
Yeah,
you
this is
alter
big.
them.
Yeah, by the way, this the MathWorks fellow who's responsible for a lot of this comes around a lot. He's been coming to the Midas seminars on Friday afternoons. So that's 4 to 5 upstairs usually, but not always. And so we have a way to interact right with the guy who's kind of overseeing a lot of this. It's here in town. That would be good to know.
Kayvan?
The person who does MATLAB here, no, I don't know. But in the past, I worked with MATLAB. I think the first version of bioinformatics Toolbox. I did the evaluation for them, and then we gave them some feedback. In Virginia, I knew the people.
The guy is actually overseeing it. It's here in town.
So if is
It's
he?
card in my office. I can't remember.
So this is the local representative.
No, this
or?
is the brains.
Excellent. So in that case, it's very often, and I know people that work with MATLAB and created some functions for them, and they inserted that into.
Yeah,
it's easy
it's
to
really good. Yeah,
create
this is
that.
really important for us to know, and start to integrate into our various classes. 575, the bioinformatics labs.
Actually, their headquarters is here.
Hmm?
Their headquarters is here, right?
So, headquarters.
Because on the street, near
That
Rack-
works. You have several things. You have
to the guy who was coming to the board meeting.
You have lots of folks here in various companies. Mathematica has a big office here. MathWorks. It's because there's the population density of mathematicians and statisticians in Ann Arbor is higher than any other city in the United States per capita. Math Reviews is here, for example. So that's why. It's a good thing. It's good.
Negar, you're done with MATLAB?
Yes.
Okay, so a very quick overview of Simulink. So I want to show you some functionalities in Simulink. So let's say you have written your MATLAB code, but you have, I'm not very fan of writing codes one after another, like scripts. At certain point, whether you like it or not, you want to do that in a visual modular form and put them together, right? Simulink, you can think of that as the modular / visual version of MATLAB, okay? So I want to show you some things in Simulink and the capabilities that we have in Simulink. Is it good, you think, Alex? Oh, this one? Is it good now? Okay. So let me show you. So basically, by typing Simulink in here, you invoke Simulink, and this is what Simulink shows you. Simulink, just like MATLAB, has libraries of systems, sub-modules that MATLAB has created or Simulink has created for you, and it gives you the capability to put them together to build the system that you want. For example, let me generate a new file. So this is really slow, but okay. So I want to generate some very simple mathematical operations and do it in MATLAB, in Simulink. Simulink has some, just like MATLAB, has some fundamental functions and capabilities that are in this section, and then you have the toolboxes. One thing for aerospace engineering, communication, computer vision, digital signal processing, fuzzy logic, neural networks, system identification. Every toolbox that you have in MATLAB, pretty much there's an equivalent in Simulink. Whether you have it on your system or not is different. So let me do something very simple. I want to create a sinusoidal function and take a derivative of sinusoidal function. I want to see how we can do that visually. I start with sources, and among my sources, I'm going to get a sine wave, right? I'm going to just bring it here. So that's my sine wave. Oops. Do you have a mouse on this? Okay. All right. So now I want to take the derivative of that, and there is like all kinds of capabilities in continuous functions, one of that being derivative. So I'm going to drag and drop this one here and take the derivative of sine wave. If I run it, you don't see that now. You will see that like it's actually taking the derivative of sine function for you. But in order to see that visually, what I can do, I can get a sink somewhere that the data is saved to, right? I can put it in a file, or I can put it in a scope, which is visually very easy to do a scope and see the results. Again, let's recap. I can get my data from a source, and that source could be a file, could be a function, could be something that I created, or it could be some ready things that they have in MATLAB, sine, random noise, and blah, blah. And I want to, when I did my operation, whatever the operation is, right now we're focusing only on derivative, but could be far more sophisticated than that. When I'm done with my operation, I want to look at the results. I can put it in the scope. Now when I run it, I can look at the scope. If this thing allows me to look at it, let me try again. This scope should show you a cosine function, which is the derivative of sine. Okay, it's coming up. Okay, you see that's cosine. The reason it's cosine is because it starts practically from 1, right? And if you don't trust me, I want to show you that we actually did that.
This is a new way to do calc, 115, guys,
So I'm grabbing.
If you are scared of calculus, there's no more reason to be scared.
So I copied the scope, I put another scope, now I'm running that again, and now I can look at the first one that was sine, and I look at the second one, which is cosine, right? So I did indeed generate a sine function, which is here, and I take the derivative, got the cosine. But now I'm going to go from this simple thing to some more sophisticated cases, okay? So let's get a branch of this guy. Okay, now let me. This thing is not very cooperative. So let me remove the scope for now. So what I'm gonna do far more mathematical stuff with this, and I will explain why I'm doing that later on. There are math operations in here. Let's say, for example, I take the absolute value of this thing, and then I will do, I don't know, exponential, e to the power of u. And I put this one in here, okay? Now I want to look at the end result of this. Let me see if I can move this. Now I need a scope, exactly. So maybe I copy this scope, put it here. And there is a reason I'm doing that. I'm just not playing with the functions here. So let's run it again. And so this is the scope 1. If I look at scope 2, it's like it's a function, okay? Now, the beautiful part of Simulink is that if I'm happy with the function that I created and it's doing what I need to do, I think that might be something you're interested in. All I have to do, and I keep doing that, like using the same operations over and over again. All I have to do is to create a subsystem for that. Now this thing is available. I can copy that and use it 100 times. Just think of, I can tell you about like a project that we did with a group of people. Is like creating the simulator of human physiology and having like differential equations for cardiovascular system, for respiratory system, blah blah. Many blocks that you have in there, they're very similar to each other. All you have to do is just change a couple of numbers in there. So you don't need to actually create that and repeat that and repeat that. All you have to do, make a bigger and bigger and bigger modules of that and put it together. If at any point wanted to have access to what's in it, you just click on it and it will show you the content of that. But in reality, you really all you need to have is the main one. Let me go back. Okay, for example, majority of the simulations that I've seen, control people, feedback control engineering people, electrical engineer, they do a lot of simulations for power plants, for control systems that they have on the valves and in refinery and blah blah. So you look at one big system, which has only 5 elements in it, and that's the entire refinery. And then you want to click on I don't know about refineries, but if you collect a power section, then it opens another one. Then, like you want to look at room 5, you click on room 5, it gives you all the valves and pressure gauges and everything in it. The idea of Simulink is that you can modularly generate a good simulation environment for something that is highly modular by its nature, like human physiology and so on and so forth. So you have very quickly, I want to show you some of the capabilities that you guys might be interested in. Of course, you can.
One quick question though first.
Yes.
So, if I've already written
Uh-huh.
something in MATLAB, is it
Excellent question.
Okay.
Excellent question. The question, let me predict the rest of it. If I've written something in MATLAB and I'm happy with it, can I create a module for that in Simulink and connect it to other things that I do in MATLAB and Simulink?
Correct.
Exactly. That's the reason they created Simulink. So let's say the image processing project that people in my lab are working on. Let's say at certain point you want to put it as a much bigger project, and this is just one component. Then 5,000 lines of MATLAB becomes only one component in there, and then you can repeat it anytime, as many times as you wish. Excellent question. So let's look at, so you have like neural network, you can have all kinds of statistical analysis that you want to do, but I just wanted to show you something that I think might be more interesting for you guys. So let's go to System Identification Toolbox. Oh, what is it doing? Got stuck. No. Let me, I went to the wrong one. Okay, anyways, so let's go to Estimator. Let's me models. Okay, so let's say okay, the functions that, have you worked with Box Jenkins or nonlinear control? So let's not do that because the estimators in here, I'm not sure if you might be familiar with. But let's say, for example, you want to do autoregressive model of a function, right, or a signal, a time series. All you have to do is essentially add that function in here, and that function, as you're doing, makes an estimation of the signal that is coming at every point. If you want to relate an input to the output using Box Jenkins or AR Max or something like that, you can get one of these components and feed it with the input and the output in the system. And as you're running the simulation, every component is modeled by Simulink for you using like linear and nonlinear models. This may take longer than I expected to do that, but that's essentially the capabilities of Simulink. There are so many libraries of Simulink that are available out there, and if you go to Matlab forum, you can have access to all of that. Many systems like human physiology or whatever, it's been already simulated and they're openly accessible for academic purposes. So at any point, if you're interested to do something related to like human physiology, for example, all you have to do is create your own Simulink and put the Simulink function that they have created as a subunit inside your system. Okay, so this library is really extensive, and you can find practically anything you want modeled with Simulink. So we have probably a couple of minutes for questions.
Is there an API to that so you can call from outside of MATLAB?
Yes, yes. In many cases, we actually call, we write Java functions, and then we call Java functions within MATLAB.
No, other way around.
Like a
Oh,
Java
you call,
program
you call MATLAB within that? Yes, you can do that as well.
but you have to.
You have to purchase the toolbox that they, for anything MATLAB charges you, and that's like the challenge of using something that is not open source, even for distributed computing. So if you want to run it on multiple machines, you can have the code, but unless you purchase the distributed processing, you cannot run it on multiple machines. But if you buy that, then you can easily put it on multiple servers. You can call MATLAB inside many systems. If you write it, or commercial systems out there, if you're familiar with National Instrument system for LabVIEW, which is the standard system used by many labs to collect data from real world and whatever, LabVIEW does exactly that. You can call MATLAB from within LabVIEW and run anything you want to do. But again, you need to purchase something on top of that to give you access to the API.
What is the your very short demo is quite slow.
This one is very slow. It's like it's an access time that is slow, not processing time. Processing time is slow if you're not a good MATLAB programmer like me, right? If you don't,
It's slow compared if I don't write it in matrix form. So
it would be horrible if you don't write it in matrix form. There is no comparison between C++ or even Java and MATLAB. It would take what it. So I have written algorithms, sort of commercial level algorithms in MATLAB that took 1 hour to run. But when we translated that code, and I put this asterisk on top of that translation, when we converted the code into C++, it was 20 seconds, right? Even though the one that we wrote in MATLAB, we tried to do as much as possible, do like matrix calculation, not to put a lot of if and thens and stuff like that. But yeah, if you can write something in C++, you should do that. But at the design level, when you're accessing your design, you're putting some ideas together, and you need to have access to general level commands. It might be easier to define it in MATLAB and go to C++. I kind of anticipate your second question. What is the complexity of writing something in MATLAB and go to C++ version of that? There is something, an open source system called OpenCV, and people who did it, created OpenCV, they try to go to MATLAB functions and create equivalent of that in C++. So a common practice, whether it's good or not, I don't know about that. People,
after it translates,
you have to work with OpenCV. It's not that everything is completed. That's why I'm saying translation on conversion. You have to work with that. And some of the functions that you think they're equivalent in MATLAB and OpenCV, they're absolutely not equivalent. Right? But the easiest way is to often generate something in MATLAB, test it, and if you don't want to commercialize the idea or like make it available to people through MATLAB, use libraries like OpenCV or something to convert it to C++ and give the C++ version to people. But that's a lot of work, I can tell you that.
So it looks super easy to put these things together. Is there any sense of typing or contracts between the data types and transformations? Is there anything that protects me from trying to add a matrix of phone numbers to a matrix of zip codes? Or is that just?
Can you explain more? I want to make sure I understand the question.
Some data transformation and prototyping environments, you can say the thing that is being emitted by this component can only be plugged into these other components.
MATLAB gives you an error. For example, let's say, for example, this thing expects a vector of 3 dimensions, right? 3-dimensional vector, and you're feeding like 5 things. Immediately, MATLAB gives you an error. And if you go to the error, it's not very easy to decipher that sometimes. But if you go to the error, it will tell you that there's like mismatch of dimensions there. Or the mismatch of type. If something is expecting only integer and you give it like a real value, it will give you also the same kind of. And not just in Simulink, in MATLAB the same thing happens. So if I'm running in command line and I'm giving an illegal input to the function or expecting something from the function which is not what it's supposed to provide, you'll get an error. It's not. So remember, MATLAB doesn't have is like integer versus not. You don't have to define the variables. Just like what Negar said at the beginning. You don't define something as integer or floating point or whatever. Makes it a bit difficult at certain point to know what exactly you're doing. You have to pay attention to that.
For a certain level, what you were asking, the answer is because the matrices have numerical types, but making like phone number type, yeah, there's no semantics. Yeah, that's a different, higher level abstract. I don't think.
Yeah, MATLAB has a symbolic toolbox which does dealing with like all kinds of symbols, letters, and everything. That also gives you an error if you feed something that they don't expect in the as their input.
I'm interested in reading more about these 20 fundamental functions in MATLAB. Do you have any recommendations of like
Just go to MathWorks and start. They have demos that go hierarchically. The first level of demos that talks about linear algebra, the matrices, those are the fundamental ones. I think not now anymore, but like a decade ago, if we look at MathWorks publications and everything, they were taking pride in creating everything based on very few fundamental functions, right? So saying everything is fundamentally created based on only a few functions. I don't know where you can find that, but I would say the best way to start with is looking at the demos on linear algebra, the things that Negar covered in her presentations, like matrix inversion, matrix. One more thing to tell you about is that in the last minute, some of the things, and this is the discussion Jeff and I had in the past, some of the things that you have in open source code, they're like they're free, they're fantastic, but the accuracy and reliability of some of the things that you have in open source is kind of sometimes questionable. I think Yanfang Guan, who's a faculty here, did something with the inverse function of Matlab versus what is available in Python. Okay, I think her group did that. They compared the functions that you have to invert a big matrix, right? People who are in physics, in astronomy, and they and in recently in bioinformatics. Right. So the question is, who can invert the matrix better, right? Because that's the fundamental part of anything that you do with linear algebra, right? And what the discussion that Jeff and I had was how fair the comparison was with what Yanfang has done. But Yanfang, I don't know the details. You can ask her. She came up with the conclusion that MATLAB was far more accurate in inverting a large matrix. She did like an extensive comparison of that than what you find in open source. Because, like, you can ask Jeff found like some discussion forums and things about that. That, like, depending on the type of matrix you have to use a different algorithm to get like a better estimation of inverse. For these things, I often trust MATLAB not to give me bad results. It's like relative, because there's a high level of quality control over the fundamental functions in MATLAB. If you go higher and higher, I would say it's less and less. But with fundamental functions, you have like accurate calculation coming out of these commands. Jeff, you want to?
On the other side of that, how does she know that the MATLAB one is better?
I think she got the inverse and then multiplied them and find whether we get identity matrix or not.
There's three different methods. The other thing is, should you be really using inverse?
Go to the dentist too.
That's another very good question.
The numerical people out there say you do it using a solver unless you really need it. Because depending on the numbers, you can have this huge spread effect, and just like a teeny little error in the small values can really mess things up. But the solvers do things in a different way. So yes, analytically you can write equations and say I can take the inverse, but practically, numerically, computationally, you shouldn't do it that way.
Yes.
And even in that documentary, I remember that they said it's better if you solve ax equals b. It's better to solve it by x equals a left divided by b instead of calculating the inverse. Because even inverse has a lot of computational overload and is not very scalable for huge matrix.
Yes. But I make the argument, I agree with all of that, but I make the argument when you're using any solver, whether you like it or not, at certain point you're doing an operation which is similar to inverse. And the accuracy inherited in inverse calculation is present, but not as bad as some algorithms for inversion calculation.
If it's not open source, we can't know what they do.
Majority of, some fundamental ones, that's a very good question. Some fundamental function, you cannot get access to that. But anything else, all you have to say is type.
Yeah, it's just opposite of, but we don't know how they implement things. We can't verify anything.
But majority of them, if you say type that function, it will go down to those fundamental functions that you have, right? It will show you how they've done it, except for the very, very important fundamental ones. Okay? Thank you very much. Appreciate it.
Thank you. It's fantastic.